Hello, welcome back to the complex arctangent series. This is part 2. We'll be focusing on complex arguments today. And I was going to do this whole part as like one video, but after looking at my notes, I realized it was probably going to take a while. So I'm actually splitting part 2 into part 2 and 3. So that means our whole complex arctangent series will have 3 parts. I'll be splitting them in terms of r less than 1 and r greater than 1. So today we'll focus on r less than 1. But before we get into that, I wanted to go over the homework problem I put in the last video. I'm not going to work through all the steps because it's literally the same computation we did in the previous video, just with different bounds. So remember that the process was to get the formula for this integral, because what I told you in the last video was I gave you my intuition as to why I thought this wouldn't have a closed form, though even though we know that the integrals from 0 to pi and 0 to 2 pi have closed forms, that this one would not. So you basically repeat the same process. That was the point. The same process as I did in the last video. So first you start off with the real part of log 1 minus I r e to the I theta is 1/2 ln 1 plus r squared plus 2r sine theta. Then you integrate both sides from 0 to pi over 2 because those are the bounds we want. And on the left side, after you use a series expansion, you'll get some series there, basically, some infinite sum. And then on the right side, you'll have an integral, which then you want to transfer from, you want to change variables from r to alpha, setting alpha equals 2r over 1 plus r squared. And then you'll get, you'll be able to isolate this integral because it'll appear on one side and then basically just solve for it. And then what you'll end up getting is you'll get this. It's plus. It's 1 minus this. So yes, as you see, this doesn't have a closed form. It looks close to like a Dilogarithm, but it's not. And also notice that when alpha equals 1, like I mentioned earlier, this term becomes 1, and what you have left is actually Catalan's constant. Oh, this is 2. There should be a 2 here, I think. Yeah, there's a 2. So that's why I said Catalan's constant was going to show up, because obviously there's a sum in there. So yeah, this isn't a closed form, but this is the solution to this. And hopefully if you follow the same steps as I did in the previous video, you'd get the same thing. So let's get into the main topic. First, let's preface that r is less than 1. First, we want to consider the imaginary part now of the logarithm. Which is just the argument. Okay, so now let's integrate both sides from minus pi over 2 to pi over 2. The bounds are arbitrary, but it just depends what kind of integral formula you want. I found minus pi over 2 to pi over 2 to be natural just because everything that we analyze in this series has to do with complex arctangent. So I thought it was natural to keep theta in minus pi over 2 to pi over 2 because that's where, arctangent keeps its principal value. Yeah, well, tangent, I guess. Yeah, so let's just integrate from minus pi over 2 to pi over 2 on both sides. But first, let's start with the left side. Okay, and remember that this I is basically shifting our theta by pi over 2. So if we remove this, what's actually happening is our angle is not going from minus pi over 2 to pi over 2, but from 0 to pi. Okay, and then we can use the geometric series, which, remember, okay, it's minus All right, hold up, wait. I need to make sure I'm remembering. I think there's a minus, right? Because this should be sum of x to the k, right? For 1 over 1 minus x, you integrate, you get a minus. Yeah, that should be it. So then it's x to the k over k, I think. Yeah, okay. And this only works if the modulus of x, I should have used z, is less than 1, but this guarantees that our little x here does have modulus less than 1, so we don't have to worry about that. So that means this equals, now I'm going to exchange the summation and the integration as usual without justification, because who cares? Oh, we have a minus. It is, oh yeah. Okay, so our x here is r e to the I theta, so that means we have r to the k over k. We have to keep the theta stuff inside the integral. So that means we have e to the I k theta, which, if we use this imaginary part, and let me pull this minus in here, that means we'll have minus sine k theta. This minus is convenient because it lets us integrate nicely, which will just be like this, which we can use the Dilogarithm notation, because here we have nothing like, we don't have that messy alpha term like we did in the homework problem. So we can just write this as Dilogarithm of minus r minus Dilogarithm of r. Nice. So let's put this back and then work with the right side. Okay, so let's do the most obvious thing. Let's make the argument just the arctangent. So arctangent of imaginary part over real part, which, let me just write this. This equals arctangent. Imaginary part is minus r cosine theta. Then we have 1 plus r sine theta. I did this in the first video as well, if you don't remember. I recognize the minus sign, we'll deal with that later. So that is one thing we could use. We could substitute this in here and we'll have an integral formula for this, just when you pull the minus out, and yeah. But personally, I don't like the kind of generalized integrals where you have a single parameter in more than one place. That motivated the previous videos, like substitution, to go from r to alpha, because then instead of having r in 2 places, you have it in 1, because otherwise you have to like check if it matches correctly with wherever else it is. So I don't like that personally. So I'm seeking to rewrite this in a better way, in something that looks nicer. So here's what we're going to do. We're going to abuse the fact that arguments have a property where the argument of a product of complex numbers is the sum of the arguments of each of them. So how are we going to use that? Well, let's look at this. We know that 1 minus ir e to the I theta, if we just factor out e to the I theta, is this. Okay, right? This is just very clear. Those two are equal. So this is the same thing as this. So this is a product. So let's just use the argument tools to, split it. So the argument of this is clearly, hold on, let me spell it out explicitly. So that means this equals theta plus the argument of this, which is, we can just use the arctangent stuff again. You have minus r minus sine theta as your imaginary part over cosine theta. And then we can remove the negatives at the top. Let's turn this into a minus. So you might be wondering, so are these two equal? Yes, they actually are. For theta in the range that we defined it, these are actually equal. You can also show this by differentiating this with respect to r and then integrating with respect to r, as long as you know the initial condition of r equals 0 gives you 0. But this I find to be much more like a much more attractive form because r is only in one place. So yeah, let's stick with this as opposed to this. But I do think this was actually kind of cool. You can rewrite like any arctangent in terms of like, basically you can look at an arctangent, see what imaginary and real parts the inside is corresponding to, and treat it as like an argument. So then you can use the argument rules to make a product into a sum. Yeah, so we can put this here. Which actually, I'll just spoil it. The theta is odd, so when you integrate it from minus pi over 2 to pi over 2, it's just 0. So we can also just take out this minus, put it on the other side. So that is to say, after we move the minus to the other side, that means we have dialog r minus dialog minus r keep in mind this is for r less than 1. You'll see how r greater than 1 actually messes stuff up in the next video. Like it greatly complicates things when r is greater than 1. Plus, well, what am I doing? That was the previous form. It's just cosine. Okay, so this is one formula. What I find kind of nice about this is if you notice that like this r is supposed to be small, right? Less than 1. So what you basically have is like arctangent of almost tangent theta. You see what I'm saying? Like if this r wasn't here, this is just a sine theta over cosine theta, which is tangent. So it's kind of neat how like you have arctangent of almost tangent theta, so it almost cancels, and r is what, you know, separates the cancellation. So I kind of find that cool. I don't know if you understood what I said. Hopefully you did, but yeah, this is the integral formula you get. And it was pretty simple to derive too, like as long as you knew the trick to get the arctangent expression, which I admit is pretty obscure. But either way, this is a cool formula, but we're not done yet. What we can do is, okay, I could use this form, or I could use another. Since I know you can do it with the other way, this is also equal to, remember as we said before, this was the original form we had it, without any tricks. And the minus sign has already been moved to the other side, so we're good. Let me check my notes, make sure everything agrees. Yes. Okay. Now, here's a little cool Easter egg in this whole problem. Like, you know we're dealing with Dilogarithms, and something very close to the Dilogarithm is the Basel problem. So, is there a way we can maybe get the result for the Basel problem by doing this? The answer is yes. And also, I think Michael Penn has a video where he does something like, he's also looking at the argument of a complex like logarithm or whatever, and he gets the Basel problem from it, but using like geometry. So this isn't like an original result. or anything, this particular part with the Basel problem. Of course, it's not original. Someone solved it already. But I just want to show you how you can actually get the Basel problem solution from this analysis. So remember we said r is less than 1, but how about we push the limits a little bit, because we know that the Dilogarithms will converge at r equals 1. So why don't we just set r equals 1 and see what happens? So that means, so Dilogarithm of 1, okay. I'm just going to have to write this in the summation form. So Dilogarithm of 1 is just this. And then you're going to have minus so that means this equals the integral from minus pi over 2 to pi over 2 of that thing, but with r equals 1. Maybe you didn't even need to use this. Maybe you could have used this, but I'm just familiar with the method for this one. Okay, now, I'm not going to actually work it all out myself because it's kind of tedious. I'll leave it as an exercise to you. But you can actually show that just with some trig rules, assuming that theta is in this range, that this right here, this cosine theta over 1 plus sine theta, is actually, what is it? Tangent pi over 4 minus theta over 2. And since theta is in the proper range, you can confirm yourself that theta in here will be in the proper range for us to just cancel it out. So what this actually is pi over 4 minus theta over 2. And theta is odd, so that's going to go away. So that means this is just pi over 2 integrated like this. So that's just really pi over 2 if you treat it as an even function. This is really unnecessary, but helps for computation. This obviously is just pi squared over 4. Okay, nice. And what do we have over here? So we have the Basel problem, which I'll just call S. Yeah. So we have S. Oh, wait. I don't need to do all that. We have S minus, and how does this relate? So if you notice, how can we relate this to the Basel problem? So if you're basically subtracting the odds, so if the full Basel problem, if the full sum has, positive values for even and odd terms, but here you have negative values for the odd terms, it's effectively, Actually, there's a better way to do this, right? You could use the eta function. Do I want to use the eta function? Now, okay, we'll do it the manual way without just using the formula. Anyway, so if the whole thing is just all positive terms, but here the odd terms are negative, that's basically taking the whole thing and subtracting twice times the negative terms, right? Not just to cancel them out, but to make them negative. So that means you have S, right? So that's the Basel problem minus 2. And then, so 2 times the odds. This would be this. I think there's a shorter way to do this. I'm literally doing this on the fly. Like, I remember I did this before, but I don't have it written down. So then here it should be the odd terms I said. So it's this. Right? The whole thing minus twice the odds. Yeah. So that should give us this. And now the odds are just the whole thing minus the evens. So 2. And then the evens, that's just, here, I'll spell it out. It's just like that, but the thing is we can factor this as just 1/4 s, right? Because of the 1/4 comes out and it's just the same thing. And this is 3/4 s, and this is 3/2 s after you pull in the 2. So if you know pi squared over 4 is 3/2 of s, that implies that s, which is the Basel problem, like this, equals, that would be pi squared over 2 divided by 3 is pi squared over 6. So it's a known result, but you can use these arctangent tricks and argument tricks to get the Basel problem if you didn't, if you wanted to hand derive it yourself. Yeah. So is there anything else I want to cover for R lesson 1? No. Yeah, so this video is a little bit shorter because, like I said, if I included the R greater than 1 part, this video would be very long. So we're not going to do that. I'm going to save it for later. So as you see here, the arguments with R less than 1 give you a nice little formula for this integral, where it's arctangent of almost tangent theta, as well as solving the Basel problem for you. Yeah, that's pretty much all I got. I'll see you next time.